So let us now address the three questions that we have for our framework, right? So for our framework, what we wanted to minimize, right? So we had the L of W was equal to, and then we had this hinge loss here, and this was of the form 1 minus just our prediction, normalized by the label, and then we had lambda over 2. Right? So now we already saw how we can write a function, so this max function between 0 and that as an optimization. So we can also write this to be the following, right? And so instead of this plus, we just write this as the max, right, over the alpha n 0 and 1, right? So each of them gets its own alpha value here. And then what we have, then we're having alpha n 1 minus yn xn t w, and then we're having plus lambda over 2 w. I guess we have typically this squared here, right? Okay, so fine. So now we're having, this is an identity, right? We haven't really done much. So now what we're interested in is, of course, at the end, what we want to do here, we want to do the minimum over W. So there will be the min over the W. And also here we have the min over the W. And we can put the max here over all the alpha now in. We can here put the max maybe outside, right? So we have here the min over the W and then max over the alpha. Okay, so the first question, okay, like that we can find a suitable function. Well, at least we found a function. Whether that's a good function, we don't know yet, but we found a function. And by example, it's easy to come up with other such formulations where we replace some basic function with some formulation of a maximum or something. So now the next question is, and that's more interesting, or let's put this up. When can we exchange the two? Okay, our plan will be that we exchange the two. And then we can do actually the minimization over the W explicitly. And we can write it down in explicit form. And then we get rid of one minimization. Then we still have the maximization over the alpha. And that we can then do not explicitly, but at least there's something we can do. So the question is exactly this thing here. Okay, when can we exchange the two? Okay, so in general, if I give you a function at a g of, let's say, W and alpha, and then clearly, let's see what to want to do. Let's assume I first minimize over W. So let me call this W prime and W prime. So clearly, right, if I give you any function, if I take the function here and on the left-hand side I minimize it over all the W prime, then I will have this inequality, and this will be true for all the W and for all the alpha in the domain that I'm interested in. Is that clear? Just taking the function on one side, I minimize over something, right, that can make things only smaller, right? So far, so good. Okay, so next what I can do is, this is true for any W and for any alpha, right? So what I can now do is, let me maximize this over the alpha, and let me also maximize this over the alpha, right? Since this inequality was true for any W and any alpha, right? For any fixed W, this is still true, right? Any objections? Fine. And of course, what I can do now, right? This is true again for all W. So now I can still take the minimum over the W. Right? And so now, of course, whether I write here W prime or W doesn't really matter. So this is always true, right? So one way to remember it, well, the easiest way to remember it is exactly to do the derivation like I did. The other one is you can just remember that kind of the innermost thing wins out, okay? If you first do the min versus first do the max, okay, the min is smaller, okay? But the easiest thing is to really derive it always if you have some doubts, okay? Good, so this is always true. Now, it's not always true that you have equality, okay? But it is true when the function looks like a saddle point, okay? Equality. So if the function looks like a saddle, so let's just see what that means here. So if we're looking at the function up here, right, the function that we're having, so let's first look independently in W and in alpha, right? So you know, what we're having here is in the W, right, we're having just a W squared, so that's convex, right? So in W, the function is convex. And if we're looking at the alpha here, right, then in the alpha, the thing is just linear, and hence we can say it's concave. Is that clear? So the function that we're dealing with is convex. If the function is convex in one of them, in the W, and concave in alpha, and that's true for our case. And then you have still two other conditions. The regions where these things are defined, the regions where for the omega and the W have to be convex and compact. Okay, so compact just means it's like some, for us, it's just some bounded, has to be just bounded. Okay, so for example, the alpha is just in the box, right? And the convex is, again, in the box, of course, it's just convex, right? You can take any 2 points. They're still going to be in the box. So in general, if this condition, so they have to be one convex concave, and the other, the region itself has to be convex and compact, then indeed you have equality. And I can't draw it on the board, but in the notes you see this looks like a saddle, right? If you ever seen a horse with a saddle, or saddle without a horse or whatever, okay? It looks like a saddle, okay? So it's in one region, it's concave, and the other one would be convex, okay? And so if it's of that form, then indeed, first taking the min and then the max versus first taking the max and then the min, you get the same results. Good. Okay, so let's assume we are in this, we are in this situation. So now let's see what we can do. Okay, so this means now this is equal to the max over the alpha here. And we have the min over the W. Okay, so what's the next thing we should do? Right, we hope now that we can do actually the minimization over the W, exactly or directly. So how do we minimize over the W? So think of alpha just being some fixed number, okay, some fixed vector. How do we minimize over the W? What do we do? What do we have to compute? Whenever we do minimization, always we compute the gradient, right? So let's compute the gradient. So what is the gradient here, right, with respect to W of this cost function here? Well, let's not write it down because the whole thing would be the minimization. So what is the gradient itself? let me forget about the min and the max. So we're having n is equal to 1 to n. So it's a gradient with respect to w, right? So this means alpha n times 1, what do we get? 0, okay? And then we're having here minus this. This is just some constant. This is also just some constant here. And so what is the gradient of this expression here? So we're having the alpha n, getting a yn. Need some help? What is the gradient? Sorry? Okay, so we are just xn, right? And then what is the gradient of the last part? Is this, and then we have still the w, right? And so this thing we need to set to 0, right? So this means this we can do explicitly, right? W is 1 over lambda of the sum n is 1 to n of alpha n, yn, xn. And just, you know, so that later on we don't need to write that much, we can write it again in compact form. So it's 1 over lambda. And so these vectors xn are now column vectors, right? Remember the whole matrix X is, these are rows, so we need to take the transposed. So we're having X transpose. This is now the whole data matrix here, right? And then we still need to do the Y and the alpha. And so one way we can do it is that to write it is like this. This is the alpha vector, goes from 1 to n, okay? And then this is a y. So, I mean, there are many ways of writing it down, but let me just put this here. So the alpha is here just a vector with alpha 1 up to alpha n. The X transposed is here something that has n times d, where every column is one of these guys here, right? And then we just need the y. And the y, we can just, one way we can do it is just take a diagonal matrix. And on the diagonal, it has these values y1 to yn. Okay, it's just one way to write it down. Okay, so now we have explicitly the minimum. We have done the minimum already. Okay, so we have to check that it's minimum, but we've done it. So now, if we plug this in, okay, so what does this give us? So this means that now we still need to do the max over the alpha. And the claim is the following. So this is n is 1 to n. And what do we get? So what we will get is this alpha n. We have still this. And then we get yn, x, and t. And now the w will have to plug this in, right? It's 1 over lambda. So we have here somewhere a 1 over lambda. And then we're having here x transpose, but it's the large X, the Y, and the alpha. And then we're having here plus lambda over 2. And then we're having here 1 over lambda X transposed Y alpha. Sorry. Okay, and so if we plug this all in, we can see that we can write this whole thing in the following way. So there will be the vector 1 times the alpha. And then we get, and actually this thing here and this thing here gives us the same thing, except this is, there's a factor 1 over 2 lambda in here, and there's a factor minus 1 over lambda. So we get in total 1 minus lambda. And this will just be whatever we have here. So this is alpha transposed y transposed, which is the same as y, x transposed y alpha. Okay. And so the point is that this whole thing we could just write as a Q. So this we could just write like this. Okay, so this is just some positive definite matrix. It's just a product exactly of two matrices, you know, left to right. So this is a very nice matrix itself. And so this is now the optimization that we have to do. Let me just check that I didn't miss any factors. Okay, looks more or less correct. Good. So now we have seen that we have from one minimization problem, we now ended up, instead of this one minimization problem where we had to minimize over the W, we ended up with a maximization problem that we ended up maximizing over the alpha. You know, in general, there's no explicit expression for this, but what we can do is we can solve this by what's called coordinate. In general, it's called coordinate descent, but here, since we want to maximizing, it would be coordinate ascent. Okay, so all this function does, all this algorithm does, is very simple. The alphas here, they are in a nice box, right? Every alpha is in a square. So all we do is we start with some alpha, and now at any point in time, you pick randomly some n, some dimension of the n's. Okay, so one random of these alphas, and you minimize along. You know, fix all the other ones, and you minimize along for that alpha, okay, in the box between 0 and 1, okay? And then you replace that position. And now you do this repeatedly, and that actually converges, okay? So this will solve that problem. If you're interested in more exactly about these things, you can look at Martin. I guess it's this semester, actually, or next semester, I think. Martin has an optimization class, and you know, he would talk all about, you know, algorithms like this or other ones. Okay, so we're not going to spend a lot of time on talking about the optimization, but it's a very simple algorithm. Okay, that at any point in time you simply pick one coordinate, you optimize along that coordinate, pick the second, you know, pick another coordinate, optimize along that coordinate, you go on. That's it. Fine. Okay, much simpler even in stochastic gradient where you need to compute gradients. Here you always just have basically one-dimensional thing that you have to do. Okay, so what I still want to talk about is the following. So there are two things that I want to talk about. So if you look at this cost function here, right, then there's something that's quite interesting. And what is interesting and what makes this, and this will be exactly the segue of what we're talking about next time, what is interesting is that the only dependence of this formulation on the data is via this matrix here, x times x transposed, okay? And so this function, or this matrix here, kx times x transposed, this is often called the kernel. Okay, so that's just a name that historically has developed. It's called the kernel, and so, yes, please.
Why is the one transposed?
Sorry? Why is what transposed? It's just the inner product here, right? I mean, this is just the sum of the alphas, right? It's just an inner product, right? It's a vector. It's the all one vector. That makes sense? Okay, that's it. Good. So why is that? You know, why is that interesting? So first of all, what does this? You know, let us look at this a little bit more in detail. So that's just x times x transposed. So let's just look. X was again n times d. X transposed is D times n. So this means that the kernel, right, has dimension n by n. Right? So this kernel here has dimension n by n. And so the only thing that this optimization depends on is exactly the inner product. So what are these things? It's exactly if you're looking at the ith and jth entry here, then this is just the inner product between the data vector xi and the data vector xj. That clear? So it's a matrix in which xith, jth entry is exactly the inner product between the I and the jth vector, right? And so what it says is that this only depends on all the possible inner products between these feature vectors. Okay? So this will be the key for next time, because we will see that this is right now, so if we're looking at this entry k, I, j, right, then this is simply the x I transposed times the xj, where these are the feature vectors. Okay, so it's just a simple inner product. And what we will see is that there's a very nice way of thinking of more general things. So remember that originally what we had said is you take a feature vector, and maybe the feature vector is not good enough. Maybe you want to add polynomials. Maybe the feature vector is x1, x2, but you want to extend it to x1, x2, x1 squared, x2 squared, x1 times x2, whatever. You want to make it larger. Okay? And when you make it larger, then now in the larger space, it's still a hyperplane that we're using, but in the smaller space, you can do much more interesting things, right? Circles, ellipsoids, whatever, right? So sometimes it's nice if we have this extra degree of freedom to be in a higher space. Now, of course, if we are in this extra degree of higher space, right, this can cost us a lot. Well, if we just add 1 or 2 components, not a big deal. But let's assume I have a vector of length 10, and I want to compute all possible terms of degree 2, right? This quickly, this goes quadratic, right? Suddenly we have something maybe that has 100 terms in there, right? Gets suddenly computationally costly. And we'll see that there's a very nice trick where we can basically work in this higher space without actually ever having to go in this higher space. And the key will be exactly that we'll start with a formulation like this, where we have these inner products, and we do what's called the kernel trick. And the reason it's called the kernel trick, because that's the kernel, and there's a trick, okay? And so that's what's called the kernel trick. We'll see that basically computationally, we can sometimes work in a much higher dimensional space, sometimes in an infinite dimensional space, right? But actually, it's just like we're pretending to work in it, but the actual computation we have to do is just down there, okay? So this will be something that you will hear all the time, and so it's interesting to see it in one concrete example, and that's what we'll do next time, okay? So that's why this formulation is nice. Now, the bad point about it is that this is an n by n matrix, right? So, now it depends. Remember, you had 2 dimensions. You have d and you have n. Often, sometimes d is relatively small, and you might have 1 billion examples. Okay, then it's, of course, not so good a priori that now you're working in n by n dimensional matrices, right? You much rather work by d matrices, but unfortunately, that's how it works. Okay, but sometimes it can also be that maybe you don't have so many, maybe you have many more features, right? Most of them useless, but you just have them, and not so much data, right? Then perhaps it's actually not such a bad idea to do. And in addition, with this kernel trick, you can work in this one higher dimension. Okay, so that's why it is of interest to do this formulation. Okay, not always. It's not always better to do it like this rather than the other one, but sometimes. But what is still good to see is this will give us now an interpretation when we go back to this picture. So irrespective if we want to use this formulation or the other one, it will give us a nice interpretation, and will also tell us why this is called support vector machines. Okay, so let us go back to this picture that we had. Okay, so what did we have as a picture? We had something. Okay, and so we had things like whatever. This was the thing here. And then we had a margin, right? So maybe let us not pick something that is separable. And then we had some kind of a margin, right? So now the claim is that this alpha vector, okay, the one that will optimize this, the claim is that the alpha vector will be sparse. So meaning the one, so it means most entries are 0. Okay, so when we do the optimization, it will turn out that actually there are only very few of the alpha terms that are non-zero, right? They all have to be between 0 and 1, but it will turn out that only very few are non-zero. So why is that? Let us just look at, remember that for every of these entries here, there was one alpha associated to it, right? And what was this interpretation of the alpha, right? So remember, what we had is that we had alpha n times 1 minus the y n x n t w, right? So we looked at this thing here. And so this was equal, and then we had the max over the alpha in the box between 0 and 1, right? So basically, this goes back now to what we had talked about beforehand, but now we see a more explicit interpretation. So let us pick, for example, let us pick a point, for example, here. Okay, so this point would be correct, right? So this point would be on the correct side, and it's outside the margin, right? So what does this mean for this? What does this mean for this argument here? So now we have fixed the w, right? And we see the picture, and let's assume that's the margin, and we're looking at this point. It's correct, and it's outside the margin. What does this mean for this argument in here? So the one thing, without the 1 minus, this will be larger than 1. So this means that with the 1 minus, this thing here will be negative, right? And so then this means, what does this mean then? What's the optimizing alpha here? Would be 0. Okay, so for points like this, they are 0. Okay, so they don't appear here. And since many points presumably will like outside here, we'll see why it's very sparse, right? Okay, then we have other points. So we can have points that, let me make them up since we don't have them. Let's assume a point, no, that's not the right point. This point, okay? Let's look at this point. This point is correct, but is exactly on the margin. What does this mean for the argument? To be exactly on the margin must mean that it must be 1, okay? And so, so it must mean that it's 1, okay? And so what does this mean for the optimizing alphas? What are valid arguments that the alpha can take on? So it's not just both, because the alpha is not in the set 0, 1. It can take anything on, okay? It can take on any value. So there are some values that will be 0. Some values can be anything between 0 and 1. So it means for something like this, the alpha can be anything between 0 and 1, okay? And then we have some points inside here, right, for which this argument here is the total thing is positive, right? So this thing is smaller than 1. The total thing is positive, right? So this means what should the alpha be then in this case? It's positive, and we want, right? It should be 1, so you should get out. And so then for those guys here that are on the right side, so I guess this one is on the right side here, right? But still, the argument is positive. For this one, the alpha must be 1, right? So here the alpha can be anything in 0 and 1, and here the alpha is 0, right? And so these have different names. So these things inside here are called essential support vectors, because basically the idea is that this hyperplane is determined by only very few of these points, okay? And only the points that are basically you're seeing here. And that's, so it's called that this hyperplane is supported by these vectors, so they're called essential support vectors, and that's where the whole name comes from. Okay, not a big mystery, but it gives us a kind of clearer picture of the interpretation of this thing. Good. I think Any more questions? Well, we're done. Okay.